Okay, but one thing is still missing, which is how do we implement the partition procedure? Okay, so this right now we use this as an oracle. Okay, again, remember, what do we want from partition? We're given an array and we're looking at the subportion of the array, the subarray, only between S to T. And what we're going to do is that we're going to use the last element in this subportion. Okay, so this is the entire array. This is the portion that we're interested in. So I'm always going to use the last element as my pivot. Okay, and my output is that basically for this portion I'm interested in, I want to put everything smaller than the pivot to its left and everything bigger than the pivot to its right. Okay, so we want to, for this original green portion, I want to output this. Okay, and what we return is the new position M of the pivot. Okay, so that's what we want to do. Okay. All right, how do we really achieve this? Okay, so let's again look at an example. So let's say, suppose here I'm only drawing the portion, which is array A from S to T minus 1. Okay, remember, I'm going to take the last element as a pivot, that's P. Okay, and I want to, the goal is to split it so that to the portion smaller than pivot and the portion bigger than the pivot, and we return its position. Okay, its index. Okay, how to do that? And what I'm going to describe to you, you can do it in different ways, okay? But what I'm going to describe to you is an in-place operation. Namely, other than this input array, I'm not going to, allocate a new array. I'm only going to need a constant number of extra memories. Okay, so I'm still going to operate on this array. So in-place operations is usually preferred because that means that you are reducing the memory usage. You're not allocating new arrays. Okay, what if your array is super huge, right? All right, so what's the idea? We want to figure out, I basically want to, what I'm going to do is that I'm going to go through all the elements in this array, okay? And then I'm going to gradually collect everything smaller than P to one side, and then followed by everything bigger than P. That's what I'm going to do, okay? So I'm going to maintain, as I scan through the array, I'm going to scan the array from left to right. And as I'm scanning through, I'm always going to collect everything smaller than P first, and then put everything bigger than P after that for the portion that I've already seen. Okay, so that's what we're doing, okay? That also means that I would like to have 2 pointers to help me to remember that. In particular, so as I scan through, let's say, suppose right now, I'm already at this position. I already scanned through this portion. So this portion I have already scanned through. Okay, and what I want to maintain is that so far, everything smaller than P, they are put first. So they are pink color, okay, they're color pink. And everything bigger than P are green. They followed after the everything smaller than P, okay? And everything green are the portion I have not yet scanned. I have not yet processed, okay? So that's what we're going to do, okay? All right, now, as I look at the next element, so I'm going to move my process the next element, okay? I look at this element X, okay? All I need to do is to figure out where should I put X, okay? Because I want to make sure that this is maintained. In particular, if X is bigger than P, okay? So if this is bigger than P, what does it mean? It means that, well, remember, if it's, I want to first put everything smaller than P and then everything bigger than P. If X is bigger than P, then it should be color green. Well, we don't need to do anything. I simply move my pointer. So X is fine, okay? I simply move my pointer to the next element to process, okay? I still maintained the invariance that for what I've already seen, it's everything smaller than equal to P followed by everything bigger than P, okay? So no problem. So if the case 1, if X is bigger than P, very easy. I simply move this pointer, which tell me which is the next element to process by 1. So this pointer is basically, well, I'm going to call this mid barrier. This is going to separate the portion smaller than, bigger than P, and the portion smaller or equal to P, and the portion bigger than P, okay? So this is the easy case, okay? If instead X is smaller than or equal to P, okay? So here I have to do a bit of work, because in this case, where should X go? Well, X really in this case should go to the pink portion, because it's smaller than equal to. So that means that X is smaller than equal to P otherwise, okay? So then it should really go to this pink portion, okay? What do I do? Well, the simplest thing I could do is that I simply swap X with Y, okay? So I first swap these two. After swap, X comes here and Y go to where X used to be, okay? But now I move the separation point barrier pointer, because now this pointer always point at the first element, which is bigger than P, okay? So now I move this pointer to the next, because X is smaller than P. That's all I need to do, okay? So again, the intuition is that if X is bigger than, smaller than P or equal to P, then it should be the pink portion. So I want to add it to the pink portion. And the way I do this is I just swap this two. I add it to the one immediately after pink, and then also make this one pink. That's it. Okay, so this is the entire algorithm. Okay, so again, well, let's just go through this in example. Okay, so let's say that I want to perform partition on this array. Then what we do is that this is our P, our pivot equal to 8. Okay, now what does the algorithm do? I'm going to have two pointer, okay? The pointer, I'm going to use, one pointer is pointing, I call this, the blue pointer is going to pointing at the first element, which is so far for what I've already scanned, this is the first element that's bigger than P, okay? And I'm also going to use the red pointer to point the first element, which is unprocessed. I haven't yet processed, okay? So at the beginning, they are all at the first position, okay? What do? I look at the next unprocessed number. Now this one is 12, which is bigger than P, which means that, okay, in this case, all I need to do is that I simply move the red pointer here, and the blue pointer still remains here. This is the first element that's bigger than P. Okay, so that's step one. Next, we look at this element. Okay, so this is the first element we haven't seen yet. This element is smaller, so 5 is smaller than 8. What this means is that now I need to move 5 to the pink portion. So far, the pink portion is empty because we don't get anything smaller than this, okay? Remember, what the algorithm does is that it simply swap this one with the first element that's bigger than bigger than P. So I swap 12 and 5, and then remainder remains the same. And then I move this. So red pointer move to the next, and the blue pointer also need to move, because now this is we find one which is smaller than P. Okay, next is 3. 3 again is smaller than 8. So that means that we perform the same. We swap this one with the first element, which is bigger than P. So we get 5, 3, 12, 9, 7, 8. And the red pointer move to the next one, and the blue pointer now also move by 1. Okay, next 8 is bigger than 9 is bigger than 8. That's a good case. What this means is that I simply move the red one here, because we found one which is bigger, so we only increase the green portion in the previous slide, and the blue pointer, the pointer separating, so the part that's smaller than P remains intact in this round. Okay, and I don't have space anymore, so you just continue this way. So that's how the partition works. Okay. All right. Questions? Okay. And as I just went through in this example, our algorithm needs to maintain 2 pointers. There's a middle pointer, which I'm going to use L to represent in my code next page. It basically separates all the numbers smaller than P from those bigger than P that we have seen so far. Okay, and the AND barrier, it basically points at the first unprocessed number. Okay, it separates what already been processed from those that's not yet processed. Okay, so this is a 2 pointer. That's going to be the a variable R in the code that I'm showing. Okay, and what I have here is exactly the pseudocode for what we just described. All we do is that start from S. I'm going to scan. So at the beginning, the mid pointer and R both stay at S, and then we're going to process the array elements one by one. Every time we look at the element we're processing, okay, if it's smaller than the pivot we're looking for, that means we have to do that swapping operation, okay? So exchange this current one with currently the mid barrier, the one that's basically the first non-pink element, and meanwhile we move the mid barrier pointer by 1. The increasing the AND barrier R by 1 is automatic in this for loop. Okay. In the end, I forgot to say, after we process other than the last element, suppose here, after we reach the last element, right now we already maintained everything smaller than P and everything bigger than P. Okay. In the end, we need to put the P also in the correct position. Okay. So what we do is that we simply swap P with currently, this is my mid barrier L. I simply swap the last element with this element, so that now after this exchange operation, we have everything smaller than P, then we have P, and then we have everything bigger than P. That's it. Okay, so this is the entire procedure for partition. Okay, note that in the code that I'm giving you, I'm always using the last element as pivot. Okay, sometimes you can also write code where you can use a different element as a pivot, or you can supply the input can contain a pivot. The index for pivot can be an input, okay, but it's not needed, right? All right, so this, as I said, is an in-place operation algorithm because you see, we just swapping some numbers within the same array. We never need to allocate more than constant memory slots other than the array itself, okay? And the time complexity is also easy to see because for each element, when we process each element, we just check whether compared with the pivot, and depends on whether it's bigger or smaller, we either just move the pointer or swap 2 numbers and then move the pointer, but both takes time only constant. Okay, that means that the total time complexity of this algorithm just depends on the size of the subarray we're looking at, which is proportional linear to the size. This means that it's to the size of the input subarray we're looking at. Okay, all right, so that's the partition algorithm. And with this, we basically now have a complete quick select algorithm. Okay, all right.